DeAngelis with Gavin Quindell, Josh Castro, and Natalie Sales Campos. She had to leave early, unfortunately, for a class, but we are here presenting testing seal strength. So today we'll be discussing how we could apply hypothesis testing to ensure the quality and safety of medical device packaging, an important area in the healthcare industry as it directly affects our patient safety, right? All of our safety. So the scenario we have today, is as a quality engineer within the medical packaging industry, you're tasked ensuring that the heat seal treatment on medical trays are within a wanted range. So within a how do you say, a possible range that is not too soft to where it's gonna no longer be stable, but also not too tough to where when you open it, it's gonna fly everywhere, which also will make it unstable and directly affect the safety of the patient. And we want that range to be within about a pound of force. And we collected our samples from, or our mock samples from various randomly selected manufacturers and randomly selected manufacturing sealants. That way we could ensure no bias, whether it's with the manufacturer or just a certain palette of packaging. And Gavin will take us into the steps of how we're going to pursue that.
Hello, my name is Gavin Quinville, and these are the steps that we are going to go through to get our sample mean, our hypothesis testing to really understand what we are looking for. So here's the steps. So to find the heat seal strength of the machine, we use hypothesis testing, which is a statistical method used to help identify whether a sample mean is different or within a wanted value in our case. It is our case is going to be 1 pound of force. This is a way for engineers to be able to make decisions based on data on situations such as the heat seal strength of a machine. So for our null hypothesis, we want it to be equal to about 1 pound. So we're going to calculate our sample mean and standard deviation, and this will tell us if the standard deviation is big enough to signal a real problem within the machine, or what the variation in the seal strength is to calculate like the risk involved with the machine, and to calculate more error and to fix the machine with whatever is going on with it. So the standard deviation for our machine was 0.205 pounds. This is simply telling us the variation of the seal strength between each tray, which we had 30 samples, so that's between each sample. So it was 0.205 pounds. So, and this is the normal behavior for the machine. If the machine has a lot of natural variation, a small difference like 0.052 is not surprising. So you won't have to mess with the machine or change anything to it. But if the sample mean is super high, say it's like 1.3 standard errors or above 2, then that's when the engineers go in, look at the machine, recalculate all the data, and fix the problem. This takes us into our two-tailed test. So we used the two-tailed test, and our answer was 0.086, which is 0.012. And then this leads on to our conclusion.
We compare the p-values of 0.05, and from this is a significant value. This helps us decide whether we will reject the null hypothesis. And then, so this will, based on our evidence, we have failed to reject the null hypothesis. And since there's no evidence to prove the mean seal strength, since it's going to be more or less than the 1 pound force, so then our meal seal strength of the machine will be within range, and then this will mean that our machinery and the device packaging is non-sterilized. So this will mean that everything in the packaging is like safely secured. And there would be no risking the patient safety. This is why we use hypothesis testing. And so then our weaknesses and strengths, our strength is data, and then our weaknesses is the substance. And this is our works cited.